All right, so the first thing is what happens when we apply torsion. What we end up happening when we apply torsion is we get shears on those planes. So if you have torsion that's applied as I'm showing, the first thing that's going to happen on an element, if you're applying torsion like that, and then like that, is you're going to see corresponding shears if you were to analyze a little element in this shaft. So if you have torsion as shown, this torsion will cause an upward shear, that will cause a downward shear. Now, if that was all that was happening, that element would be out of balance. It would start to spin counterclockwise. So to prevent that, you'll get shears that develop on the other two planes like that. So when you apply torsion, as I'm showing, what you end up with is a shear element in the shaft. So torsion is associated with shear. So what we get then is we have this formula, that tau max, and what that equals is tau xy also. They're the same thing, and that's TR over I, okay? And the I is subscripted with a P because it's calculated in a polar mode, okay? Now, the other thing we got is that sigma x and sigma y are 0. There's no normal stress. So once we have that, we can go and start doing all the biaxial stuff. Okay. So are we good with that? Okay. Now the biaxial formulas simplify a good bit because the full biaxial formulas involve a lot of stuff with sigma x and y, and that zeroes out because sigma x and sigma y are 0. So what you end up with are simplified biaxial formulas, right there for sigma x1 and right there for tau x1, y1. They're simplified, they're on the back of the formula sheet. And they are 96 and 97. So there's special biaxial formulas for torsion because they're much simpler than the full ones. So they're often just written as separate formulas, even though they're not. They're the biaxial formulas with sigma x and y being 0 is what they are. Okay? Because there's no normal stress in the x and y directions of the shaft. Right? And depending on how you fabricate a shaft, you might want to know what the stresses are at a given angle. See? Okay. Now, if we want to know what the maximum stresses are at a 90-degree angle, or excuse me, the maximum shears occur at 0 and 90 degrees. And they're equal to tau xy cosine, they're equal to TR over I. Okay. That's where the maximum shears occur. And as it turns out, the maximum normal stresses occur 45 degrees off of that. Because if you remember from the biaxial stuff, the principal stresses and the maximum shear stresses are 45 degrees apart. That's why this is happening. Okay. So both tau max and sigma max are TR over I. However, they occur 45 degrees apart. Okay. All right. So let's have a look here. Let's say we've got a shaft, and maybe make a sketch of this somewhere. So we got a shaft like this. And we're going to do that to it. So we're going to apply a torsion to it, as shown. Draw up a square element in here and show the shears, all 4 shears on that element. And those are going to be tau max. So why don't you just sketch up, what's the maximum shears going to look like on that element when you sketch it up? So which way are they going to point, I guess is what I'm after. And this is just a visual kind of analysis. Just look at how the torsions are going. The shears point the same direction. And then the other 2 shears will meet in the corner. Right, we got something there? So is tau xy going to be positive or negative on that element? What's that? Negative? Positive? Okay, yeah, because this torsion will cause this shear to do that, right? This torsion will cause this shear to do that. They both point, the one on the right points up, the one on the left points down. That's positive torsion because if you think of it being like a couple, that would rotate that element counterclockwise. The other two torsions would meet in the corners, right? So you would have a shear pattern like that. Good? Okay. Okay. So how about drawing up an element that shows the sigma maxes? Where do the normal stresses act? The maximum normal stresses. If you were to draw up an element that showed those, how would you draw it? Would it be a square as I'm showing at 0 and 90 degrees? So where would an element be where the maximum normal stresses are acting? Is it? I'll give you a hint. It's not a square. It's not at 0 and 90 because the maximum normal stresses don't act at 0 and 90. Yeah, it's going to be a 45 square, right? Y'all okay with that? Okay. So it's going to be like this. All right. Now, one pair of those is going to be tension, and the other pair is going to be compression. Okay. Now, let me show you a trick to figure out which one is which. You can always calculate. You could plug in sigma x1 for 45 degrees and use a positive tau, because tau xy is positive, and figure it out. But you can also do it visually. And to do it visually, I'm going to do some stuff with color, so I hope everyone is okay seeing color, because I know not everybody is, but let's see. Start with that. So I'm going to draw those two shears the same color, and then I will draw the other pair of shears a different color, and maybe I'll squiggle them, so if you don't see color too well, you'll see the squiggles. There we go. So there's all four shears. Now, if you were thinking in terms of vectors, which I want to emphasize, this is not true because these stresses are not vectors, okay? Forces are vectors. Stresses really aren't, and we're drawing stresses, but all the same, if we visualize them as vectors, if you add those two straight brown vectors in a vector sense, which way would they point? And if you make the two into one vector, if you find the resultant of those two vectors, which way would it go? Like, give it a compass direction. Northeast? Y'all good? Up right? There you go. Okay. Now, how about if we do the two green ones and add those together like vectors? I'll go like that. All right. Now, let's do a little different color combination here. I'll get in touch with my artistic side here. So what are we going to do? Okay, we're going to go, I don't know, I'm going to go with squiggles on this. We're going to do that. So those are blue. And then we're going to go another thing. We'll go purple. And really go like that. All right. Like that. Now, if you add the two blue ones like vectors, which way do they go? They go like that, right? And then if you do the two purple ones like vectors, they'll add up like that. So that's how you can draw the maximum tensile and compressive stresses if you have a shear stress. You take two adjacent stresses, you add them together like a vector, and you put them on the adjacent plane, okay? Which is important, so you know where to put them. So basically what I'm doing here is I'm creating a plane. I think of it, I like to draw with CAD a lot, that's something I do. So I would connect the midpoints here and put a diamond inside of the square. That's how I get my 45-degree plane. That makes it easier to see how those stresses combine together and which plane they would act on, maybe. Does that help? I don't know. You with me? Now we could calculate that and find it too if we wanted, but I like the visual thing, so I can just draw it, okay? So y'all okay with that? So what I'm saying here is our maximum normal stresses are going to act like this. Good? Okay. So what I'm thinking about is my shaft going to fail? And if it is going to fail, how will it fail? That's what I've got in my mind's eye. That's what I'm thinking about. Right? And as I've said a few times, when you're in school, the problem is doing all the calculations. But when you're working, that is not nearly as big a problem as it is in school. The problem when you're working is saying, I'm designing this hydraulic jack. What do I got to design it for? What does it look like? How's it going to break if it breaks? And maybe it's as simple as I just better reinforce that because that looks kind of weak to me. It's not quite as like you're not just sitting around doing tensor calculus all the time when you're working. Believe me, okay? You're looking at stuff and you're figuring it out. And these days, how many of you work in SolidWorks? You done stress analysis in SolidWorks? You think maybe? So, all right, and that's just going to get more and more prevalent as your careers move on. You got to be able to kind of anticipate what the issues are. That's really the deal when you're working, to me anyway. It's not, the analysis isn't quite so hard anymore because you've got tools for that, But anyway, okay, so let's have a look at this. Now, I've got some simple materials because obviously I can't break mild steel. I'm pretty strong, but I don't think I can do that. But mild steel is ductile, okay? They make it purposely to be ductile because mild steel is what you make structures out of. And you want structures to be ductile because you don't want them to just fracture and snap like cast iron would. Or cast iron is high carbon. It doesn't deform much. Or glass. You don't want something to shatter. You want it to gradually fail because it absorbs more energy. It's a better failure mode, okay? So ductile. Now, if I apply that torsion to that mild steel, how will it fail? Well, let's kind of think now. Ductile materials. What are the modes of failure are what? We've got 3 modes of failure, right? We got shear, we got tension, and we got compression. Now, also just think about it. If you take a ductile material and start twisting it, what does it do? Yeah, it's not that fancy, right? If I just take a ductile material and I just go like that, what's it going to do? It's just going to keep twisting, and eventually it's going to do that, right? And what angle is that roughly as you cut your way across from my original twist? That's kind of how about, look at this one. It's probably better.
Oh,
yeah, I think, it's obviously it's not a perfect failure. It's a lab experiment, right? And what kind of failure is that? What doesn't this clay, what breaks first on the clay? It's shear, yeah. See, it's just shearing straight across. That's a 90-degree shear failure. If you look at the cross section, what's happening there? If you take this and model it kind of like that, what's happening is you're getting a bunch of little shears building up in there as I twist it. And this material just doesn't handle it very well. It can't resist that. This material doesn't handle anything very well, obviously. But anyway, shear is probably the weakest mode for steel. Okay, you good? Okay. So that's what's happening there. Okay. All right. I got a brittle granular material. okay? Now that would be something like cast iron, which they do make shafts out of. That obviously is a pretzel. So here, you can, I brought some. So why never run their own torsional test, see if you work in the pretzel factory, you might have to run the torsional test. If you're gonna eat the pretzel, I guess you hand sanitizer too. So just grab a pretzel and pass it around. Let's apply a torsional test to these things. Here we go. Let's see what happens.
You're a pretzel expert, huh? Yeah. Oh, look at this. You don't know about these, huh? These might be the heavy duty kind, okay? These
Yeah.
might be cast iron.
It might be, yeah, you don't know, I don't know.
These are the cast iron pretzels.
Okay. Yeah, look at that. Okay, now it's not perfect, it never is, but see, that isn't a coincidence. We're getting consistency as people are failing their pretzels here, see? And it's coming out the same every time. It's not, I mean, there's not one of those that's going to break straight across. And I don't know if you know much about like bone breaks, spiral fractures. Those are torsional fractures on a long bone. That's what this is too. And if you look at the textbooks and what those look like, they don't just break straight across, right? Yeah, it's flu season. I don't mess around with that, man. I don't like getting that stuff. Okay, so I've got some styrofoam here, and I always have to look at this to make sure I'm doing it right. But this top one will come over the top and then the bottom. Now this isn't the old, this is a little bit flexible, this stuff, so it's not perfect. I used to be able to get drier, kind of more rigid styrofoam. But see that? That's at an angle across. Okay? And that'll happen every time. Okay? So see that angle there? That's a pretty classic spiral fracture there. Now you might have different quality of pretzels. I don't know, how, but actually they're pretty consistent. They're a granular material, right? They're like concrete or cast iron. And see how that kind of wrapped a little bit? But see that angle? It's pretty good 45 on the one I did. Okay? There's actually a real shaft, okay? Cast iron. See how that failed? Now there has to be, there's a 45 and a 45. So what kind of failure is that? What's going on there? Go back to your sketch. So go back to that sketch you just made, because I tried to make it, I think so, we drew the sketch in this mode. What's the stress that's pulling that thing apart on that angle? I think so, yeah, okay. Y'all okay with that? We good? Tension, right? Because that plane went right here and we pulled it apart. See, that's a normal stress on that plane. Pulling it apart, that's a tensile failure, okay? Like that. That's tension. It's tension, okay? Doing that. Y'all okay with that? All right. Okay, last one, we got a hollow thin-walled tube. And they make tubes hollow because it saves on material costs. It saves weight and material cost. So how do you think a hollow tube would, if it's thin-walled, how's that going to fail if you apply a torsion to it? What's the weak mode for something that's thin like this? Compression, yeah, because it buckles, right? All right, so let's just do the analysis here. Okay, so this shear is going to go up or down, this one, based on the torsion I'm applying. Up. The other one will go down, the other two meet in the corners. So based on that sketch and the one you already made, which way do you expect the compression to act on that? Because remember, the compression will act on a 45-degree plane. So kind of like that, just kind of put a diamond in there inside the square. Which way will the compression go? Like that. Good? Okay. This one, I got this one is a little longer. Those short ones, the ends kind of interfere, but the longer pins with it. buckled. It's not 45 because these ends are kind of influencing a bit, but it's just the right idea there, okay? So see how those compressions push in into that buckle? So that's a compressive failure. See, right on that line where the compression is, that pushes in, and it buckles that thin walled tube. Oh man, I know it's so late. I'm sorry about that. All right. Sorry. So there we go. So we'll finish this up. Now, no school Monday, so we will finish it up Friday. But remember, there's no school on Monday. Okay. Oh, if you want a pretzel on the way out, like, help yourself if you like pretzels.